Okay, so after you saw the coolest demonstration ever in physical chemistry, now we can do our review. Any questions, preguntas?
Yeah, what concepts are going to be on
What? What?
concept?
Concepts? All this stuff. Let me ask concept questions here. All right, let's get some concept questions. Okay. What was this equation for? What good was that?
Excitation energy?
The what?
Excitation energies?
Excitation energies?
The energy between different levels?
Yeah, they were trying to explain what? What were they observing that they were trying to explain? I mean, you're right, but not really the direct observation. They're trying to use that simple equation, that one equation, to explain what you guys just saw.
Oh.
Right? Why is there only in that plot, and you saw it, it was even numerical, right? Why are there only these for helium, for example? Okay. Oh, they have hydrogen though, so we were looking at helium, so we have to have a hydrogen lamp. But all right, so that's what it was used for. So the Bohr frequency condition, here's an expression for it, but it pretty much just means what? How does that correlate with this? Right, is this emission or absorption intensity here? Emission. So that means the molecule must be what, Jeffrey? Or the atom must be what if it's going to emit light? Excited. So how did it get there? Well, one way is the Bohr frequency condition. It could have absorbed energy of the exact right energy, right, between those energy levels. So you can kind of see what they are, right? Just measure the difference between the wavelengths and convert it into energy. Okay. But there's other ways to excite it. So it's kind of moving on beyond what this simple little math equation was, right? And it was just playing with math to get the right answers. Now they're trying to figure it out. Okay. And then they started talking about the hydrogen atom because, right, it could be solved exactly by the Schrödinger equation. So you had all these solutions, these exact solutions. So hydrogenic atomic orbitals. So here's our quantum numbers. What were the names of those? N, L, and M sub L.
N is the principal.
Principal quantum numbers, N. L is angular momentum quantum number. And M sub L is? That's M sub S.
Orbital?
Starts with an M. Magnetic quantum number. So and we have the rules for all these. I think we talked a little bit about this. If it's a hydrogen atom, there's just pretty much what two subatomic particles are we talking about?
Proton and electron.
Proton and electron. So the reduced mass, since we're not talking about translation, we're talking about rotational motion, we need to be talking about reduced mass instead of just the mass of the entire molecule, the mass of the entire atom. This really comes down to be, like if you call this the mass of the proton, the mass of the electron, the reduced mass that you're supposed to be using in all these expressions will really just come down to be what?
M sub 1.
M with a P or M sub with an E?
E.
E, the lighter one. Yeah. And there's, I think that was a concept preview question or something like that. What's the Bohr radius? What was the?
84.6 picometers.
Yeah, so many picometers, 50 some picometers. But what did it was?
A0.
Yeah, it's the most likely position of the
Hydrogen.
electron in a hydrogen atom. That's kind of the meaning of the Bohr radius. So with these hydrogenic atoms, the energy, we have these quantum numbers. Which quantum numbers do you have to specify to get the energy for these hydrogenic atoms? All of them?
Just N.
Just N, right? The answer's right here. All right, just specify an N, you can get the energy. Okay. Oh, let's see. Oh, here's a good one. Why are these? What's going on up here? It says continuum. What does that mean? Continuum.
Behaves like classic physics.
Behaves like classic physics. Yeah, it's true. All energies are possible, because where's this electron now? What's going on? Right down here, what's going on?
The electron's bound.
It's bound. It's
Quantum.
yeah. It's what type of force is going on down there? Like, why is it negative? Negative energy. I mean, what the heck? All right, negative HCr over 4 and whatever. Why is it negative? That was their convention for what type of electrostatic force? Attraction. That was their convention. So positive meant repulsion. So you have overwhelming attractive forces in here. So that's what's holding it. That's what they're saying. Potential energy is negative. Okay. And now here it's free. It's unbound. Right? There's no boundary conditions. If there's no boundary conditions, it's unbound. There's no quantization of energy, because the boundary conditions are what give rise to quantization of energy. You have to have boundary conditions. You have to have boundaries. Let's see. How do you find the most probable radius? Because we have this radial distribution function. And what it is you take this eggshell, right? Take this eggshell, right? And that's all its thickness is, like an eggshell. And you just, whatever radius you want it at, you set it there, right? And you see what P of R is, right? That's the probability of that electron being there. So there's a distance from the nucleus where it is the most probable, right? That's where R equals what again? R equals, what do we define it? A hint is that this is 1.
R equals 1.
It's divided by A naught, so R would have to be at the peak. How do we define A naught?
Oh,
Where'd it go? The Bohr radius, where'd it go? There it is. You told me. Right?
So R has to equal Bohr radius.
At the most likely location, yeah. That's why they give it the special Bohr radius number, where at this peak, that distance is, you said 50-some picometers. So at some 52 picometers, they call that A naught. They call it the Bohr radius. And if you plot R divided by A naught at 1, that's where your peak is. So what they're saying with this radial distribution function, it's just what's the most likely radius in a thickness dr in an eggshell for this hydrogen atom. And so if you want to find the most probable radius, what you do is, okay, where's the slope the maximum? Or where's the slope, not the maximum, where's the slope? You want to find the maximum of this plot. You want the slope to be 0, right? So you take the derivative of that function and set it equal to 0. That'd be your most probable radius. And where do you get these radial wave functions? Yeah, look at some table. So we can write the full wave function, our radial wave function, and we had this last time, spherical harmonics. That's a chapter 12 table. So as a radial part, now we're talking about 3 dimensions, so we have 3 directions there. Hey, how do you find nodes? I don't know where nodes are. Nodes coming up here somewhere? How do you find nodes? This is a good one. There's homework questions on this.
Total node equals.
How do you find the location of nodes?
Oh, the probability density is 0.
Well, yeah, if I gave you a nice plot and then you'd look at it and see that there's no problem, yeah, that was true. But if you actually had to tell me where they are, where are these radial nodes? You have to set the function equal to 0. Oh, what function? Oh, you just look it up, right? They're talking about the 1s orbital. Well, find the radial wave function for the 1s and set it equal to 0, right?
So do you set the derivative of PR to 0
to find the most probable radius? Because that's what this function gives you. This function gives you, right, the probability of it being at these distant, the probability of that electron being in that thickness of an eggshell, right, at some distance. And so that's what this function gives you. Well, if you want to find the most probable or the maximum or minimum of any function, let's just set the slope equal to 0, right? Or you can take the second derivative and where that's maximum, but where nowhere it equals, second derivative has to change sign. It has to be, first derivative slope is 0. Second derivative where it changes sign, the curvature. That would have to be 0 too, because it has to pass through 0. But second derivative is twice the work, so why? Just stick with the first derivative and set it equal to 0. And then see how they're, again, hydrogenic atom. We hit it when we finally wrapped things up. We kind of went full circle, and with that handout that we did at the end, because we started with just it was almost like a game. This thing was, is you just randomly play with things to try to figure out and reproduce this. There's no meaning behind it. It's just a game, right? And you get it to match. Well, now we started going into the quantum mechanics of it, which is really just statistics, and we came up with some selection rules at the end, and we didn't have to play the game. We could actually derive term symbols for every single one of these states and use the term symbols. Using these selection rules, we can say what term symbol will go to what term symbol, like figure out what the ground state term symbol is, an excited state term symbol, and see if the transition will occur. And you have these selection rules, right? So we kind of explained all this. So we had forbidden, allowed transitions. There's a lot of homework there. Okay, and then we moved into mini electron atoms. And it's really not so bad, I think, because of this. What was so special about closed shells? And they're trying to picture it here, this idea of a closed shell. The net angular momentum is zero. And why is that such a big deal? Because when you start trying to couple all these electrons, where are these rules at? These Klepsch-Gordon, look at that. When you start coupling all these electrons, you don't have to worry about the ones that are all paired up. So because their net angular momentum is zero. So don't even include them. So it really made life a lot easier. So it sounds, oh, mini electron atom sounds really tough, but it's not that bad at all. Okay. Some fudge factors here. We never really talked about this too much, I don't think. Is there anything that I could pick on? What is this a picture of? Yeah, 2s orbital. And are they trying to show a 3D, or is it supposed to be flat, or what? They're trying to make it look 3D. They're trying to make it look 3D. The only hint there is their axes, X, Y, and Z axes, right? So Jeffrey, how the shaded regions mean what?
That it could be in there?
Yeah, the electron should be in there 99% of the time. Well, if that's the case, how can it get to the center?
Would have to emit like a photon? Or is that just one orbital?
This is all just one orbital. There's an angular node. I mean, how the heck? Think of the slinky. Remember when I brought in the slinky? And you remember making nodes on it? How do I make more and more nodes with the slinky? Increase the frequency, right? You remember that, Jeff?
Yeah.
Yeah, increase the frequency. Okay, so, and this is with a macroscopic object, but there were certain regions in there where you didn't see any movement at all as a node. But yet, you had motion over here. So, it's very much a wave property. It's only a wave property where you can have constructive and destructive interference like that. Does matter act like a wave? de Broglie says it does. And he says it does even big time the smaller you get. So yeah. And it's quantum, it doesn't, since they're talking about an electron and you see in a table, oh, there's so many kilograms in an electron. Yeah, really small, but there's a number for it. So we think of this electron as a particle. How the heck can it get there? Right? And it's just a quantum mechanical phenomenon. You're never going to observe it here. It's going to spend 99.99% of its time here and out here. Like I said, at the microscopic world, man, very strange things happen. They just don't make sense. From our way of looking at things. But this stuff has yet to be proven wrong, so we'll keep going with it. Our life is very good, actually, because of quantum mechanics, all the stuff that it's helped us with. Okay, this was kind of the concept preview. You remember Hund's rule? All right. What expression do you write for this ionization energy? If you're going to make up a homework question, and what's the mathematical expression you're supposed to write or think of when you think of ionization energy? I don't think I give this to you.
Is it the photoelectric effect equation?
Pretty much.
Yeah. Oh, okay. So like E.
Or in English, you'd say the
H C over lambda equals.
well let me put it in English. Hc over lambda. That's the energy of the what?
Of the photon.
The photon. That has to equal
The kinetic energy of the electron.
the kinetic energy of the electron. That's ejected, right? And
Plus the
ionization, the energy to get kicked out in the first place. All right. And then there's the equations for all that stuff. Well, what's so special about a Rydberg state? And I guess you kind of got to realize we're talking about many electron atoms now. We're not talking about hydrogenic anymore. So this is the equation for hydrogenic. If you got the same answer for this mini electron atom and it totally matched, oh, that's called a Rydberg state. It just matched what a hydrogenic was. Usually it doesn't. Right? It's mini electron. Okay. Then we spent a lot of time coupling. So know how to couple.
So what is J again?
Yeah, good question. What's the name of? Okay, remember. Go back again. What's the name of L?
Angular quantum number?
Angular.
Principle?
Angular. Not angular quantum number. Angular momentum quantum number. Okay, angular momentum quantum number. Little s? Spin. Full word. You can't just stop and say spin.
Spin orbit coupling.
Spin moment, spin quantum number?
Yes, you're halfway there. Spin.
Orbital?
Angular. This is all about angular momentum. A concept that is really, really hard to recognize. Because Jeff could be wrestling, right? That's all momentum and torque. That's all momentum and torque. We don't see any angular momentum anywhere. The only time you experience is with a bicycle, and you don't even realize angular momentum's going on. So angular momentum, this is all about angular momentum. So again, little l, or big L, right? If there's more, if you couple the little l's, you get a big L. But whatever, you call it what?
Angular momentum.
Angular momentum, quantum number. Little s, or big S if you couple them. Spin, angular, momentum, quantum number. Okay. J. Whether it's little j for one electron or big J for many electrons. A hint is, well, the Clebsch-Gordon coupling. L plus S all the way down to L minus S. It's angular momentum, but it's total. Total angular momentum. So we're trying to couple the spin, angular momentum, and we're trying to couple that with the spin is angular momentum. So you're trying to couple that spin angular momentum with what? And we'll get total angular momentum. We're coupling spin with, we call it spin blank coupling.
Orbital.
Okay, so we're good. So we're trying to couple spin angular momentum with orbital angular momentum. And then we get J, which is total angular momentum.
So M sub L is magnetic angular.
Yeah, but now we don't even really care about little m sub L and m sub S anymore because we're more interested in just coupling and getting spin quantum numbers S and orbital angular momentum quantum numbers L. So I think if we went further and did different applications, we might go further. But so here's our equation for spin-orbit coupling. Figures 1329. Trying to see what the red and the blue are. I'm interested in that. Right. Yeah, those arrows are magnitudes, but of what type of orbital are they talking about? Oh, they're both lined up. I think that's what they're trying to say. They're trying to compare the blue with the blue and the red with the red, right? So high energy, right? They're both pointing in the same direction, red with red, blue with blue. So it's kind of like pushing a north end of a magnet up against the north end of a magnet. Whereas in B, right, blue with blue and red with red, they're coupled. Well, coupled's the wrong word. They're because they're both coupled. They're paired up, right? Lower energy. lower potential energy. My goodness. Thank you. Okay.
So the big S still means spin.
Yeah. Spin, angular momentum, quantum number. Did we ever write all that stuff down? Oh, I guess if you use big S, we should use the word total. Right? If you had little s, it'd just be spin. Right?
It's confusing.
It does. Little l, orbital angular momentum quantum number. Big L, total orbital angular momentum quantum number. Big J, total angular momentum quantum number. Little j, I guess angular momentum quantum number. I would still call it total though, but you have to sum to get it. It is confusing. That's a good test question. Can't put the easy stuff on there. So we've done a lot of these projections. I don't think that's very hard. Writing term symbols, that for sure will be on the test, right? We never messed really with JJ coupling. What's precession?
Movement of the magnetic field.
What's that?
Movement in the magnetic field or something?
Yeah,
like that?
it's movement. It's you don't have to have a, well, let's back up a little bit. You can have precession of a bicycle wheel, right? You spin the bicycle wheel and I hold that up on the axis, right? You remember me doing that? I spin the bicycle wheel and then I held it on a string, right? And it was kind of rotating around like this. Did it stay right here? No, it started going, right? Rotated around like this, right? So that's precession. Gyroscopes, everything do it. Nature just does it. That precession of the rotational motion. And so likewise, if you have a little spinning charge, right? If it's spinning, it's going to act like a little magnet. So it'll be precessing. But it's, I mean, that's precessing here. This guy's precessing down there. They're all over the place, precessing all these different directions because they're just atoms, right? But you can get them all to line up if you apply a magnetic field, right? Because they're all acting like little magnets. So they'll all be precessing then in the same direction. Ooh. Then since energy is quantized, if you have things, they can't precess at any angle they want. The energy is quantized. So that means it's not like a bicycle wheel where I can have it precess, like this angle or fly. I can have it precess whatever angle I want. Not with small objects. So they can only precess in certain orientations. So that means they're going to be different energy states. So I can apply, magnetic field to get them precessing. But the point is I can apply some energy to it, get them to absorb whatever the difference between the energy state is, between one precessing angle and another precessing angle. Apply that energy. Get them to undergo the transition. What wavelength am I talking about now? Changing the precession angle of a bloody atom or a proton. It's a hint. If you had NMR, radio waves. Radio waves is what we're really talking about. That's what the NMR uses. And we're not going to talk about that kind of stuff that heavy onto an exam because I don't even think we talked about it that heavy here in class. So we kind of saved that for instrumental. But that's what's going on with instrumental analysis is this right here, precession.
So smaller objects only precess at specific angles?
Mm-hmm. because their energy is quantized. And they only precess at certain frequencies. But I don't think you're going to see that on the P-Chem exam, because we didn't talk about that too much. So I wouldn't worry about that.
What do we worry about?
It's just a good lead-in into instrumental analysis. I would worry about the homework. Because there's always some concepts, but the homework is where it's all at. Those handouts we did. But I think you have all the homework done, right?
But that, for problem 13,
Here's your equation sheets. Do you see these? I don't know if you have these in your book, right? Usually, so here's page 1, here's page 2. So, page 1 equation sheet, page 2.
So for problem 13.5, where it talks about the excitation of potassium at 760 nanometers and 770, can we just find the term symbols, and then since it's on the Lao translation is from J is 3/2 to 1/2, can we just plug it into the equation HC 1/2 A equals J whatever it is, and then we get whatever A equals to, and then we
So what did you get as an answer?
you use the difference of the wave numbers to get. I got for A I got 3,300.21 times 10 to the negative 9 meters,
It makes sense.
or 38.507 meters.
That's number 5?
Bottom 13.5,
Yeah, yeah, 30. Yeah, so I got A 38.5 wave numbers. That's how I did exactly what you're saying. I figured out the energy in terms of A for each transition there, or each term symbol. Subtracted them.
Yeah, so since it's only the 3/2 to 1/2, because only J's are allowed, so that's what we put in that one equation, and plug in the L's and the S and all that stuff. Yeah, that one.
What term symbols did you get? I got 2p 3/2 and 2p 1/2.
Yeah, and for the ground state it was 2S 1/2. Because it says only that the ground state at so many nanometers.
Yeah, and they said what the splitting was, right? So you pretty much just have to. I got the energy for the 2p 3/2 to be 1/2 HCA, and the 2p 1/2 I got to be a negative HCA. So you subtract those two, and you get 3/2 HCA. So that's the splitting that they were talking about, right? And then you get your A out of that, just solve for A, because you know what everything else is.
Well, in the book, there's an example 13.5. It talks about that transition of 3/2 to 1/2.
Really?
You just plug
Did it all for you?
You have to check 13.5, and if you have that transition, like it automatically goes 3.5 A. All you should do is use your wave numbers and to where A is and then find A from there. That's 13.5.
Yeah, I know where that is. Justification. I went through a lot of work to get that one. I have a whole page. G2. What the heck? 13.4. I'm getting close. Man, they hardly did anything. That's so much easier than what I did. Look at all this.
So can we just do that?
But you had to.
Yeah, you have to find the term symbols.
Yeah. So yeah, that's pretty much what I did. I found the term symbols. I think all this was just a waste of time up here. Did you find the term symbols? Yeah, that's how I did it. It's just a lot simpler than how I did it. That's for sure.
Do we turn in that handout for myself?
No, well, let's not turn in anything. So we have an exam. Oh, no. So what we're going to do is we're going to start chapter 14 on Monday, and we'll have our exam on Tuesday. So, and chapter 14, I think, is pretty short. So just be aware. You could be turning around and taking a test right after another one there. But if it's that short, we'll probably have it during class.